So here we are starting chapter 16 in Wade. This is the chapter on aromatic compounds, not the reactions of aromatic compounds, just the starting of. So the nomenclature of aromatics, what can you do to the carbons off of the ring, that type of stuff. So in this chapter, we'll talk about how to name things, how to do reactions of the functional groups off of the rings, and then in chapter 17 we'll get into reactions of aromatic rings itself. And of the 4 tests in Ord 2, the test over chapter 15, the dienes, 16, the aromatic compounds, and 17, the reactions of aromatic compounds, could be one of the easiest sections of the class, just because there's not a lot that goes into it that's different. But we can, if we have a monosubstituted aromatic ring, we can just say what the substituent is: chlorobenzene, nitrobenzene, ethylbenzene, methylbenzene, those type of names. Some of them, like methylbenzene, if you go looking for it, you won't find it as methylbenzene, but instead you'd find it as toluene. So there's the common names that a lot of them have, that is, you're more likely to find the compound if you go looking for it as. And on the test you can use either the IUPAC or the common name to name things, and that's fine. So we have toluene, phenol, anisole, aniline, benzoic acid, benzaldehyde, acetophenone, styrene. That's how you'd find most of those things. So if the aromatic ring is a substituent off of something bigger, instead of it being in the ending of being something benzene, it is a phenyl group. So here we have the aromatic ring as a substituent off of that 9-carbon chain. So it is 1-phenyl nonane, because the nonane portion is bigger than the benzene ring, so it takes priority. So it's a phenyl ring off of that, so 1-phenyl. Now if you have a disubstituted benzene, you have to figure out, is it 1, 2, 1, 3, or 1, 4? What's the highest priority group, and go from there. So in this first example here, we know it's a phenol because the phenol is in the base name, the alcohol. So that's carbon 1. So then do we go 1, 2, 3, 4, 5, or 1, 2, 3, 4, whoops, can't count, 1, 3, 4, 5, 6. We know we want the lowest possible number, so it needs to be a 5 bromo, 2 chloro, phenol, because we go to the chlorine first and then the bromine, so we get the lowest possible numbers. So how can we name these things? We have aniline, we have benzoic acid. Now make sure as you're spelling these things that you write out the name, spelling it correctly, so that you don't lose points for misspelling. Toluene, we have and toluene, methylbenzene, we have the 1,3 dimethylbenzene, or the common name is a xylene. And for the xylene, that takes into account that it has the 2 methyls on it, so we just have to say, where are they? So it's a meta 1, 2, 3, or meta is the best way, or it's a 1, 3 disubstituted one. So in the next one here, we have a substituted toluene, and off of that toluene we have a bromine on carbon 3, so 3 bromotoluene. On the next one, we have this whole group, which those of you in biochemistry have probably talked about it. It is a benzyl group when you have a CH2 off of the aromatic ring. So this is benzyl bromide. And then we have the 1-phenylnonane that we talked about a minute ago. And then here we have a benzoic acid as the base name. So 2-nitro and 4-bromo, or 4-bromo 2-nitro benzoic acid. Okay, now we can draw resonance structures of just moving the double bonds around in the ring, and that's why benzene is so stable, because you have the resonance structures you can draw. While we think about it as 3 pi bonds and 3 sigma bonds, they are not distinct pi bonds and sigma bonds. They're all a mixture of each, so it's really 1.5 pi bonds throughout the ring, and we'll get into that more as we go on. So we learned back in Org 1 that we could add bromine to a double bond, and we could get the 1,2-dibromo compound with the anti-addition. We can draw that mechanism and all. But if we just add bromine to benzene, we get no reaction. Okay, and that tells us that benzene is much more stable than cyclohexene. And this stability comes from the fact that all of the double bonds are conjugated. They're all equivalent. They're not very reactive to just doing away with a double bond. So we have to be careful still. What do we do to the aromatic ring? We don't really do much to it until we get into the next chapter, and there are only 5 reactions that react with aromatic ring. So how do we know if something's aromatic or not? The easiest way to tell is thinking about Huckel's rule and what it tells us. And Huckel's rule came down to, if the ring followed all the other rules of being aromatic and had 4n plus 2 pi electrons, where n is a small whole number, then it follows Huckel's rule, and it would be aromatic if it followed all the other guidelines. So when we look at the cyclopropenyl anion, we have 4 pi electrons. So if we put 4n plus 2 equals 4, subtract 2 from both sides, 4n plus 2, n equals a half. That is not a small whole number. This is anti-aromatic. Okay. The next one, we have 2 pi electrons. 4n plus 2 equal 2. Subtract 2 from both sides, 4n equals 0, n equals 0. Oh, look, this is aromatic. The next one, we have the cyclobutadiene. It has 4 again. It is, I shouldn't have circled that, anti-aromatic also. Just to keep them separate, we'll only circle the aromatic ones. Then if we go to furan, which we've named already, we have 6 pi electrons, 2 for one double bond, 2 for the other, and one of the lone pairs could be in one. So 4n plus 2 equals 6, 4n equals 4, n equals 1. Oh, small whole number. Furan is aromatic. Okay. Then if we go to the cycloheptatriene, we say, does it fit all of the rules of it? Is it planar? Well, it probably is. Does it have alternating single-double bonds all the way around the ring, or a continuous pi system? And we look at that carbon right there. We have an sp3 hybridized carbon because there are 2 hydrogens off of it. So we know with that sp3 hybridized carbon, we don't have a continuous pi framework. So this is non-aromatic. Okay. And then the cyclooctatetraene has 8 pi electrons, so 4n plus 2 equals 8, 4n equals 6, n equals 1.5. Well, that's anti-aromatic again. And then benzene, 4n plus 2 equals 6, 4n equals 4, n equals 1. Benzene is aromatic also. Okay, so we can do this to help us decide, is it aromatic or not? So how can we, the easy way to do this, another way is we can draw the frost circles, where we draw a circle, draw the polygon inside the circle with 1 point at the bottom of the circle. Okay, then draw the horizontal line through each carbon of that polygon, and then draw a dotted line through the center of it. Okay, and that dotted line is the demarcation line between the bonding orbitals, which are below, and the anti-bonding orbitals, which are above. Okay, and then what we do is start putting in the electrons that we know we have, and in benzene we have 6, and so all the bonding orbitals are full, and the non-bonding orbitals above the line are not used, so it would be aromatic. So we did that on the previous page. You could try it again here on your own and go back a page to look at it to see what it looks like. Okay, and make sure you understand the frost circle and being able to use Huckel's rule. So aromatic compounds other than benzene, we have this alternating single double bonds in the hexatriene. It's not a ring, so it's not aromatic. We have here not a continuous system of p orbitals because we have that sp3 hybridized carbon, so it's not aromatic. And then the next one we have is the p orbitals do not overlap because the molecule is planar. The molecule has to be planar to be aromatic so that you have the overlap between adjacent p orbitals on each carbon around the ring. So annulenes are fully conjugated pi systems. The easy one, 6-annuline benzene, is aromatic. As we go along, we see that the 10-annuline is not, because of the interactions between the hydrogens on these 2 carbons, so it's not planar, and the 14-annuline is somewhat destabilized by sterics, and that's also not planar, so it is not aromatic. So the main annuline is the 6-annuline that is aromatic. And the 6 just tells us how many pi orbitals we have in there and how many bonds in the system. So a 5-membered ring could be aromatic if it has 6 pi electrons. So if we had, we've already said, if we had cyclopentadiene, it's non-aromatic because we have that sp3 hybridized carbon. If we have a lone pair on that carbon, then we could have 6 pi electrons, and the cyclopentadienyl anion would be aromatic. Okay, so because we have 4n plus 2 equals 6, 4n equals 4, n equals 1, it is aromatic. Okay, if we go to the cyclopentadienyl cation, while we have a continuous pi framework, we only have 4 pi electrons. So this would be anti-aromatic. Okay, and it depends on how many pi electrons we have, whether it's aromatic or anti-aromatic. So the next one, a 7-membered ring. If we had just the 7-membered ring with a CH2 at the top, it would be non-aromatic because you don't have the continuous pi framework. If we put the anion in there, then we would have 4n plus 2 equal 8, 4n equals 6 when we subtract 2 from both sides, n equal 1.5. This would be anti-aromatic because we don't have the right number of electrons in it. But if we have the cycloheptatrienyl cation, now we have a continuous pi framework again, but we only have 6 pi electrons in our 4n plus 2 system for the Huckel's rule. 4n equals 4, n equals 1. So the cycloheptatrienyl cation is aromatic. And it depends on what you have off of it, what the charge is in these, whether they are or not. So you have to be careful about what you have. Okay, aromatic heterocycles, perol, pyridine, they are both aromatic. Perol does have a lone pair on the nitrogen, but we have 3 double bonds inside the ring, so 4n plus 2 equals 6. So the lone pair on the nitrogen is in a sp2 hybridized orbital in the plane of the board, or in the plane of the iPad, in the plane of the video. So it is not in the p orbital. It's not used. So pyridine is aromatic. Perol, 5-membered ring, would put the lone pair on the nitrogen in an sp2 hybridized orbital, so we'd have 2 lone pairs, that's 4 electrons, and the lone pair on the nitrogen. So 4n plus 2 equals 6, 4n equals 4, n equals 1. Perol is aromatic because the lone pair on the nitrogen is used in the aromatic system. We can also look at other rings. Imidazole, the nitrogen with the hydrogen on it has a lone pair on it. It would need to be in an sp2 hybridized orbital to overlap with the other ones, whereas the nitrogen with the double bond off of it, the lone pair on it, would be in the sp2 orbital in the same plane as the imidazole ring. So it is not used in the aromaticity. So if we were to add imidazole as a base, it would act as a base at the lone pair that's not used in the aromatic system. We can go on to polyaromatic hydrocarbons. Okay, they've been heavily studied. Naphthalene, we have the one benzene ring, but then we have another one hooked onto it. They're all planar carbons, so it has a continuous pi framework, whether it's naphthalene, anthracene, phenanthrene. They're all planar. Each of the rings has 6 pi electrons, so they are fully aromatic compounds. So what can we do to an aromatic ring? The only part that is reactive is going to be the carbon right off of the ring, the benzylic carbon. So we can oxidize the benzylic carbon, the carbon right off of the ring, as long as it has at least 1 hydrogen on it. We can oxidize it with either the sodium dichromate or potassium permanganate in heat, and we can get benzoic acid out of the reaction every time with no problem. Okay, but there has to be a hydrogen on that carbon right off the ring. If we do it to T-butylbenzene, there is no reaction because there is not a hydrogen right off of the ring. It's a free radical reaction. You have to have a hydrogen there to start the process. So T-butylbenzene is no reaction. We have to have one hydrogen. If we had isopropylbenzene, it would react because there is one hydrogen on that ring. So we can turn it into benzene. What happens to the other carbons on that benzoic carbon doesn't matter. All we're looking for is we can get benzoic acid out of that. Okay? So we can also brominate it. We learned in Org 1 lab, we did the bromination of all of the different hydrocarbons and noticed that the hydrocarbons that had a hydrogen on the benzoic carbon were much faster than all the other hydrocarbons. So we could add NBS or just bromine and light, bromine and heat, and we can brominate the benzoic carbon to give us a handle on the molecule. Because remember, what can we do with a hydrocarbon? We can brominate it or we can burn it. There's nothing else we can do to a hydrocarbon. They are not reactive. So once we brominate it to make the brominated benzoic carbon, if it's a tertiary carbon, we can do an SN2 or an SN1, excuse me, where we replace that bromine, in this case, with an oxygen by using water to add to our cation. And then that gives us the extra hydrogen on the oxygen. We remove it and we get the alcohol. So we can turn the alkyl bromide into the alcohol on the atom right off of the ring to show it happening. Now this cation is very stable because, and we don't have to draw all the things off of it, but with the cation there, we can send electrons towards the cation and keep chasing the positive charge around the ring. Remember, the positive charge has no electrons in it, so we can't move it with an arrow because the arrow is moving electrons. All we can move are the double bonds. And we have to draw the resonance arrows in between each structure, and we have to show the movement of the electrons as we're going around. So that gets us there. That's why that benzoic cation is so stable. The benzoic radical is also stable because you can resonate the radical around the ring. We can do an SN2 on this by adding a strong base to a primary or secondary. Primary is best. Benzyl bromide. We have the SN2 where the nucleophile comes in, the leaving group leaves all in one step. Okay, so reactions of benzoic halides or alcohols of benzoic leaving groups with concentrated acid and a tertiary alcohol, we can do the E1. With a strong base and a tertiary alcohol, we can do the E2. Those are the reactions we learned back in Org 1. And in E2, the base comes in, remember the sodium, unimportant, grabs the hydrogen, forms a double bond, kicks out the leaving group. You form your product in one step. In the E1, we have the strong acid and heat. We protonate our alcohol first. So we get this. The water leaves, forming the cation, which we've already shown is very stable. And then once we have that cation, water can come grab a hydrogen and form the double bond to give us our product. In the E1 or the SN1, remember you have to go through the cation every time. Don't skip any steps. Draw the mechanism stepwise and go from there. So what can we do off of an aromatic ring? We can oxidize the benzoic carbon as long as there is one hydrogen on it to the benzoic acid. We can brominate it as long as there is a hydrogen on the benzoic carbon to the brominated compound. If it's a primary halogen, primary bromide, we can do an SN2 reaction, and then from there we can carry on with the reactions of alcohols that we learned in the last chapter. From the tertiary bromide here, we can do either an E1 or an E2 depending on the reagents, the conditions we use, or we can do an SN1 to form an alcohol. And then from there we can react with alcohols as we learned in the last chapter, or we can react with alkenes as we learned way back in Org 1. So what can we do to an aromatic ring itself with a lot of hydrogen gas, high pressure, high temperature? We can reduce the benzene ring. 100 atmospheres. We're not going to go there. Don't go there. Don't reduce the aromatic ring. Leave it alone. Okay, with hydrogen, platinum, milder temperatures, all we can do is reduce a double bond off of the ring. We don't do anything to the ring itself. Okay, and we take it from the double bond to the alkane, or from the triple bond to the alkane. We learned that back in the end of Org 1, so we know those. The one reduction that's easy to do, or easier to do, on an aromatic ring is the Birch reduction, where we can reduce it with sodium, ethanol, methanol, and ammonia. And what this is it's a dissolving metal reduction. The sodium is sodium metal. It is it is not a cation. There's no charge there. It's sodium metal. So when it reacts, it loses an electron. Dissolving metal loses an electron to the ammonia solution, and that electron gets pumped into the aromatic ring. So if we were to draw a generic mechanism for this, we have that one electron that gets pushed into the aromatic ring, and we have to move the electrons around the ring. So that gave us an anion on one carbon and the radical on the other. That anion is going to go grab a hydrogen off of methanol or ethanol, whatever the alcohol is which we used in the reaction. And then we're going to pump another electron into the other side to form the anion. And then that'll go grab a hydrogen off of methanol. And in the process, we have reduced it to the 1,2,3,4 cyclohexadiene. Okay, and it's always a 1,4. Remember, when you name an alkene, you have to number through the double bond. So you have to, number 1 is on one carbon of the alkene. Number 2 is on the other carbon of that alkene. So in this process, we add 2 electrons into the into the benzene ring and reduce it to the cyclohexadiene. So if we have a functional group off of it, if we have a donating group, the only product we form out of it with a donating group is with the oxygen off of the double bond. If we have a withdrawing group, the only product we form is with the oxygen off of, or with the carbonyl off of the carbon that would have the double bond. So in this, remember, on the previous page, we drew this intermediate. So where on this intermediate would it be safest, would it be most stable to put that oxygen of the anisole? We're not going to put it on the carbon. We're not going to put it here. I'm not going to put it here because that oxygen is electron rich. It's not going to go well on the carbon that has the negative charge on it. So the only place we can put an electron rich group is on the carbon next to that, so it's as far away from the negative charge as possible. If we have that same radical anion and think about where we can put a withdrawing group, if we put the withdrawing group here, we can draw a resonance structure sending that negative charge out to the oxygen. So this intermediate is going to be stabilized when we have a withdrawing group on it. So we're going to get the negative charge on the atom that has the withdrawing group. So depending on what kind of group we have off of the ring, whether it's electron donating or electron withdrawing, is going to have an impact on what happens in the reaction. And it's all because of the intermediate that's formed in that reaction where we have the radical anion in there. Where is that anion most stable? So in an aromatic ring, remember, in the IR, we have a peak just above 3,000. May show up. You may see it for an aromatic ring. Okay, we have the 15 and 1600 peaks. For the double bond in the aromatic ring, those might show up. And then down below in the 600 to 900 region, that's the most important region for all of this, because these can be hard to see, or they don't really tell us what kind of aromatic ring it is. But if we look down here in the 6 to 900 region, we can tell what kind of ring it is, whether it's mono substituted or di substituted with a 1,2, 1,3, or 1,4 di substituted aromatic ring. They all have different things. Okay, the mono substituted peak has two peaks at 7 and 750, roughly the same size. The 1,4 has one peak at 800. The 1,3 has three peaks, 700, 800, and 900. The 900 one might end up being really small, so it might be hard to see. And then the 1,2 is one peak in the mid sevens, I want to say, like 750 or something like that. So we've talked about NMR spectroscopy back in Org 1 also, and we've done a little bit of it as we've went along in Org 2. If we have the easiest of the di-substituted rings to show, and remember, in an aromatic ring, whatever the hydrogens on the ring, it doesn't matter. The integration for that region between 6.5 and 8 tells you what kind of aromatic ring it is, whether it's mono, it'll integrate for 5 total hydrogens down there, or di substituted, it'll integrate for 4, whatever you have. However many hydrogens are off of the ring, that will all show up in this 6 to 8 region roughly, so you can tell how many hydrogens are on the ring. The easiest one to identify is the 1,4 di-substituted ring, because you have symmetry. No matter what the groups are, you have symmetry on either side, so each hydrogen is next to one hydrogen, so they would both be doublets. So in this region, if it was a para-substituted ring, you'd have 2 doublets in that would integrate for 1 each, or 2 each in that. Okay. Carbon 13, we've talked a little bit about it. The aromatic ring show up between 100 and 150 ppm. It'll show how many different types of carbons are in the ring in that region. If there's symmetry off of the ring, like say you have a mono substituted aromatic ring, you're only going to have 4 different types of carbons because you have symmetry down the center of the ring. So, and carbon 1 and carbon 4 are different because carbon 4 has a hydrogen off of it in this ethyl benzene that I'm showing here. So remember, look back to your Org 1 material. Can you draw 4 resonance structures for the following compounds? with the oxygen off of the double bond, we know all we can do is send the electrons up to the oxygen to form a negative and a positive on the benzoic carbon, and then just chase the positive around the ring. Till we get the right number of resonance structures. And this one we can draw 6. Okay, normally I only ask for 4 in a resonance structure, but we'll draw all of them just to get them all in. Send it back in from the oxygen. We reform the carbonyl and get the 3 double bonds in the ring. Okay, and remember, when you draw resonance structures, the one I gave you does not count as one of the 4 or 6 that you have to draw because I gave it to you. I don't get points for the stuff I draw. Okay, in aniline, we can't send electrons out to the nitrogen because it already has 8. All we can do is send them into the ring. So we send them into the ring and we get a double bond to the nitrogen. And then 4 electrons at a time, we can send them around the ring. I didn't use the iPad very well on this one. And then send it back to the nitrogen. And we get that. Okay, so those are the 2 resonance structures. This one is an electron donating group because you have the electrons on the atom right off of the ring. The only thing they can do is go into the ring. This one is an electron withdrawing group because you have that double bond to the more electronegative atom off of the benzoic carbon. So the electrons go out to it, and then you have a positive charge that you can resonate around the ring. Remember your resonance structures. They're on every test, and we're getting into aromatics where everything depends on the resonance structures you can draw.